Welcome back to another episode of Messing Around with Math. To kick this off, I have a simple question for you. If 3 soap bubbles combine together, what will the resulting bubble cluster look like? Would it look like this, or maybe something like this? Or perhaps all 3 of these configurations are possible. You can probably tell the answer is the first configuration, because 1, it looks the most natural, and 2, there's actually a photo of it online. I had to draw these 2 because, well, they don't exist. Anyhow, this is the only optimal configuration for 3 bubbles, because no matter what size the bubbles are, each one gets 120 degrees of space, and all these other angles are 120 degrees as well. If you adjust any of these angles even a little bit, the bubbles will immediately go back as soon as you let them. And if you have more than 3 bubbles, would you look at that, the pattern still holds. Soap films, which are shown here in blue, they're the surface part of the bubble, they always meet in groups of 3, 120 degrees apart. This happens every single time without exception, you can check for yourself. When they meet, they form soap borders, which are the white lines you see here. These soap borders always meet in groups of 4, equally spaced apart, which happens to be 109.5 degrees apart. Again, this happens every single time to every soap border, just look around this image. These 2 patterns are collectively known as Plateau's laws, and while they're not 100% accurate because everything always messes up in real life, they're pretty much fully accurate. So let's try to figure out why these patterns exist. Alright, let's start. First, let's look at something simple. Let's consider a singular bubble instead of multiple. We all know that a singular bubble is always a perfect sphere, but why? Is there something inherently wrong with a cube bubble? The answer is yes. All bubbles follow 2 fundamental rules. First, bubbles naturally try to minimize surface area. For example, if you make a bubble in a weird shape like this, it will automatically turn into a sphere because of this rule. This thing has a lot of surface area, and spheres have much less surface area, so the bubble naturally tries to spherify. But wait a minute, if you have a smaller sphere, you have an even smaller surface area. So why doesn't the bubble just get smaller? Well, because of rule number 2. The volume of the bubble doesn't change no matter what. This one is more obvious, there's no way for air to enter or exit the bubble, so it's not going to suddenly get larger or smaller. So, given this volume, which is a constant, bubbles naturally find the smallest surface area that encloses that volume. How on earth do the bubbles know that a sphere has the smallest surface area? I have no idea, ask a chemist. But yeah, these are the 2 fundamental rules, and they govern everything about how soap bubbles look. The first rule tries to make bubbles as small as possible, at least in terms of surface area. This would mean that bubbles shrink to non-existence, if not for the second rule, which ensures that bubbles maintain a constant volume. So instead of making the bubble smaller, the first rule is forced to decrease the surface area in another way, and it turns out the best way to do that is to make the bubbles round. But if you have multiple bubbles, making them round isn't enough. You also need to have some very specific angles. Yes, Plateau's laws are just a result of these 2 rules. In other words, if bubbles follow these 2 rules, which they do, they must also follow Plateau's laws. That's kind of strange, isn't it? These 2 rules seem very vague, and then, all of a sudden, you have a bunch of very specific angles. Anyway, the point is, minimum surface area only happens if these 2 specific conditions are met. If you don't have the correct angles, then that means this isn't the minimum possible surface area. You'll be able to decrease it by having the correct angles. So why is this configuration always better than this configuration? You might say symmetry, 120 degrees is more symmetric. But the thing is, oftentimes our bubbles will not be remotely symmetric. Also, this configuration is symmetric. But Plateau's laws say that this is not optimal at all, because only 3 soap films can come together, not 4. So symmetry isn't the solution. We need to try something else, and as always, a good idea is to simplify the problem. Maybe reducing the problem to 2 dimensions might do something? Let's try that. We of course need to modify our 2 rules, because neither volume nor surface area makes sense in 2D. So let's replace volume with area. The area of each 2D bubble cannot increase nor decrease. And let's also replace surface area with length or perimeter, whichever one you prefer. So our first rule is now, bubbles naturally try to minimize the total length of all these black lines. Alright, let's start testing with 1 bubble. Intuitively, the bubble should be something like a circle to minimize perimeter. Things are going well so far, this is similar to what we got in 3D. Time for 2 bubbles. This is a bit more tricky, because if the 2 bubbles are different sizes, then things get surprisingly complicated. Are all 3 of these soap films circular? It could be the case that for 2 bubbles, some other curved shape is more optimal, like an ellipse maybe. Even if we make both bubbles the same size, we still don't know what these 2 curves are. They look like circular arcs, but the thing is, we can't prove it. In fact, we couldn't even prove it back when we had 1 bubble. How do we know that a circle has minimum perimeter? You might think it's an easy question, but it took until the 19th century to solve. And 2 bubbles is probably going to be harder than 1 bubble. And indeed it is. If you search up double bubble theorem, you'll see that it wasn't proven until 2002. By the way, the proof of this theorem says that yes, all three of the circles are circular arcs, and they do come together at 120-degree angles. But since we're trying to figure this out on our own, we'll just ignore that. Anyway, it looks like even the 2D version of this problem is too difficult to prove. But there's not really any way to simplify it further. You can't go one-dimensional because there's no 1D analog of length. So how about this? A few of you might have heard of a similar problem, the Steiner tree problem. Basically, you have a bunch of points, which we'll call main points, and you're trying to connect them all up. Now of course, there are a lot of possible networks that connect all the main points, but the Steiner tree problem is all about trying to find a network with the shortest total length. See how this is similar to the 2D bubble problem, where we also try to find the shortest total length? And you might say, that's not much of a connection. There are lots of optimization problems that try to minimize length, and you'd be right, there are. So why did I choose the Steiner tree problem? Well, let's try solving it. Let's start with two main points. The shortest network that connects 2 points is a straight line, pretty simple. What about 3 main points? You might think the shortest network is 2 straight lines, but oftentimes it's better to have a network that looks like this. The strategy is no longer directly connecting each of the 3 main points. Now the optimal strategy is making a new point that does all the connecting for you. This new point is called a Steiner point, and why don't you guess what these 3 angles are? That's right, 120 degrees each. It turns out that Steiner points always do this. Each Steiner point, without exception, always has 3 connections spaced 120 degrees apart. Sound familiar? Now you understand why I chose the Steiner tree problem instead of another similar optimization problem. I should note, however, that I knew this property of Steiner points beforehand. If I didn't, I don't think I would have been able to make the connection. Anyway, the proof of this 120-degree Steiner point thing is one of the most satisfying proofs I've ever seen, so here it is. We'll start with 3 main points. Where is the best location to place our Steiner point? In other words, if our main points are A, B, and C, and our Steiner point is x, where can we place x such that ax plus bx plus cx is at a minimum? Well, we know the answer. We need to place x so that all 3 angles are 120 degrees, but we need to prove this. If you want to pause and try to solve this yourself, go ahead, but be warned, it is quite a difficult problem. Okay, here's the solution. We're going to take triangle ABX and rotate it 60 degrees clockwise about A. Label the 2 new points B' and X'. Now notice that because rotations preserve length, the length of BX is equal to the length of B'X'. Also, the length of AX is equal to the length of AX'. Therefore, AXX' is an isosceles triangle. One more thing, notice that this angle is 60 degrees because that's how much we rotated by. Therefore, not only is this an isosceles triangle, it's also equilateral because equilateral triangles have these 60-degree angles. Which means, all 3 sides are equal in length, so we'll color them all red. Alright, so far this has made 0 sense. We're trying to minimize AX plus BX plus CX, red length plus blue length plus green length, and the only thing we've managed to do is turn our diagram into a mess, whereas before, the 3 colors were neatly connected at one point. But now, all 3 colors are connected into a path between C and B'. So, if you were to walk from C to B', you'll need to walk a length of green plus red plus blue, which happens to be what we're trying to minimize. But obviously, if you walked in a straight line, you would get there faster. A straight line is the shortest path. Therefore, if we draw another diagram where the green, red, and blue lengths are all on a straight line, that would be optimal. Green plus red plus blue is at a minimum. Think about it. How would you decrease green plus red plus blue from here? You can't. This is already a straight line with no way to shorten it. Now that we've established that this diagram is optimal, let's finish the proof. Since this is an equilateral triangle, all 3 angles are 60 degrees. Therefore, this angle here is 120 degrees, since this is a straight line. Similarly, this angle over here is also 120 degrees. Now, if we rotate this part of the diagram 60 degrees counterclockwise, it goes back to how it was originally. But now we know that these 2 angles are both 120 degrees, and therefore the third one must be as well. We are done. So now we've finished the proof for 3 main points. What happens when there are more than 3 main points? How can we prove that all of these Steiner points have 120-degree angles? Well, suppose that one of them doesn't have 120-degree angles. We'll just focus on this part of the network, the part that offends us, and ignore everything else. We will only consider this Steiner point and the 3 points connected to it. But notice how this is the exact same situation as the one we just proved. We can adjust these angles into 120-degree angles, which we know is better than before. The total length has decreased. Therefore, the old network can't be optimal because we know we can better optimize it. Keep in mind, this new network isn't optimal either, because by adjusting this part of the network, other parts have had their angles changed. But that doesn't matter. We're only focused on the fact that this new network is better than the old one. Therefore, this old network can't be optimal, which was the only thing we're trying to prove. If a network has a non-120 degree angle, it's not perfect. Thus, a perfectly optimized network would need to have all 120 degree angles. With that, our proof is pretty much complete. There are probably a couple holes in the reasoning somewhere, some edge cases we haven't considered, but all the main ideas of the proof are here, and that's what matters for our purposes. So now that we somewhat understand the Steiner tree problem, we can go back to the 2D bubble optimization problem and use what we learned. First, let's try the same thing we did with Steiner trees. We'll prove that if a bubble cluster doesn't have the correct angles, then it's not optimal, it can be improved. If we manage to prove that, we'll know for sure that optimal bubble clusters must have 120 degree angles, and then from there we'll extend that reasoning into 3D and get Plateau's laws. We can also directly use our results from the Steiner tree problem, since both problems are about minimizing length. If we pick out any 3 points, we immediately know that the shortest network connecting those 3 points has the 120 degrees thing. However, there's a problem. Bubbles are round and Steiner tree networks are not. We can get around this problem by just zooming in a bunch, because at that scale everything is basically straight lines. However, I don't know what to do from here. If you have some sort of configuration like this, where the angles are wrong, sure, we know that you can reduce the total length by correcting the angles. The problem though is that the area of the bubble has now decreased, which violates fundamental rule number 2. I don't know how to get around this problem. I have no idea how to reduce the length without adjusting any of the areas. Maybe the change in area is negligible because we're on such a small scale, but then why isn't the change in length also negligible? I have no clue, so that's where I'll leave the video today. Hope you enjoyed, and I'll see you next week. Peace.